In this video, we're going to continue our discussion of the chain rule. This is part 2 of our chain rule video series, and so we're going to continue with this example. Find the derivative of f of x equals the square root of secant 5x plus 1. In the previous video, in part 1, I asked you to identify the 3 functions that are being composed here. So hopefully you were able to identify 3. And if you're just starting this video, that's okay. Can you identify what the 3 functions are? So we're going to have the outside, middle, and inside. So then let's talk about what's the outside function. So the most outside looks like it's the radical. So it'll be the square root of stuff. I'm going to be very technical here. And so we can write that as stuff to the 1/2. So that's our most outside function. Now, what is the middle function? And sometimes the middle function is kind of hard to identify. So what about the inner function? The most inside function. So here you have, so let's rewrite this as f of x equals, then I'm going to have something to the 1/2. So that something is the secant of 5x plus 1. So it looks like my most inside function is that 5x. So the middle must be secant of the x plus 1. So this is how our composition is looking. So we have the radical is on the outside, then the secant of more stuff plus 1, and then the inside function. So and that's in the order in which we're going to take the derivative then. So if I was going to write the full composition as we did in prior examples, then I would have our, let's see, how can we write the 3 functions? Before we had y and u. So now let's think about y will be then u to the 1/2. But we have a third function, so now u will be secant of v plus 1, and then v would be then the 5x. So when I want to get to dy dx, right, dy dx is going to then be dy du times, and then du, now u is a function of v, so du dv times, and then lastly v is a function of x, so dv dx. Are these the same? Yes. Notice that dimension analysis, right, our du's will cancel, dv's will cancel, even as with dy dx equals dy over dx. So this does work. And so those are our functions. So now when I take the derivative here, then dy dx is going to be the derivative of the most outside function. So it's going to be 1/2 of u to the negative 1/2 times then du dv. So this is going to be the derivative of this one with respect to v. So what's the derivative of secant? That will be secant v times tangent of v. The derivative of 1 is 0, so that one goes away, times now the derivative of v with respect to x. dv dx will just be times 5. And now let's plug everything back in. So this will be 1/2. What was u? U is secant of v plus 1. So this is going to be secant of v plus 1 to the negative 1/2. And then I have times secant of v, tangent of v times 5. And now what is v? V is 5x. So this becomes 1/2 secant of 5x plus 1 to the negative 1/2 times secant of 5x, tangent of 5x, and then times 5. So one of the things I want you to notice is that we had 3 compositions of functions. So notice that I have 3 multiplications here, right? So this is because this is the derivative of the outside function. This is the derivative of the middle function. And this is the derivative of the inside function. And so that is how we're using the chain rule. Now I did this one rewriting it as the three different functions and doing the Leibniz notation that I talked about in the prior video, Leibniz notation. But we can just do the standard way as well. So let me do that. Let me copy the function and bring it down below and do it the shortcut way without having to write out the compositions. So if this is my function, right, then I want to identify, okay, so I'm going to rewrite it at least to say secant of 5x plus 1 and then to the 1/2. And so what I'm going to do is identify the outside function is the 1/2, the middle function is the secant 5x plus 1, and then the inner function is the 5x. So if I write them out like this, I find that sometimes helpful to identify, okay, what am I, because this tells me what I'm taking the derivative of in order. So then f prime of x is going to be the derivative of the outside and then the inside left alone. So it's going to be, my outside is the 1/2, so it's 1/2, the inside left alone, so 1/2, subtract 1 here, so that's negative 1/2, and the inside is secant of 5x plus 1, so I don't touch that. Then times the derivative of the middle, right, the secant. So the derivative of secant 5x plus 1, the derivative of 1 is 0, so I'm really just taking the derivative of secant of stuff, secant of 5x. So then this is going to be secant of 5x, right, the inside stays the same, times tangent of 5x. And then now that I've taken the derivative of the middle, now I do times the derivative of the inside. The inside is just 5x, so the derivative of 5x is 5. And so notice that I still have my I have three functions being composed, so I have three products. The outside, the derivative of the outside, the derivative of the middle, and then the derivative of the inside. Now, can this be simplified? Not by much, right? We can bring the 5 to the, multiply the coefficients together and then that negative exponent, you can bring it downstairs. So the only thing really that I can do here is say 5, and then I'm going to have 2 on the bottom, and this whole thing is going to come to the bottom as secant of 5x plus 1 to the positive 1/2, and on the top I'm going to have the 5 and then the secant 5x tangent of 5x, and that will be my derivative. So one note that I want to say here, or a warning, my warning or caution sign here, is that when you take the derivative of secants or cosecants, right, those are the ones that have multiple, right? If I have secant of x, the derivative of secant is secant tangent. But notice here that I have a chain rule. So with the chain rule, you have to be careful because the inside stays the same. So if I have secant of, say, x squared plus 1, and I want to take the derivative of this with respect to x, the derivative of secant is secant tangent, right, but of the inside. So this will be secant of x squared plus 1 tangent of x squared plus 1, and then times the derivative of the inside. So times the derivative of x squared plus 1, which is 2x. But so my caution here is that oftentimes I see people say, oh, the derivative of secant of something is secant tangent, and they don't put the what the inside is. So make sure that that remains as you take the derivative of secant is secant tangent. Leave the argument as is, and then you do times the derivative of the outside. And same with cosecant, right? The derivative of cosecant is negative cosecant x cotangent x. But if you have a chain rule in there, so I'm going to go very technical here again. If I have the cosecant of stuff, that's my technicality there, then the derivative of cosecant of stuff is negative cosecant stuff left alone, cotangent of stuff left alone, and then times the derivative of the stuff. So stuff prime. So just be mindful of that if the argument inside a trig function is not just x, especially with cosecant and cotangent, because their derivatives have, like the derivative of cosecant is negative cosecant cotangent, that you don't just put x in there, that you put whatever the argument was. So like here, secant of x squared plus 1. So the derivative of secant is secant of x squared plus 1 tangent x squared plus 1. And then chain rule tells you times the derivative of the inside. Now, in identifying how many functions are being composed, let's try this example. Say I have y equals cosine of the cube root of sine of tangent of 3x squared plus 1. So what I want you to think about is how many functions are being composed here. And then can you identify the order in which you would take the derivative? So going back to that one where we had 3 functions being composed, right? We rewrote it so that I could identify my outside, middle, and inside, and then that's the order in which we take the derivative. And because there are 3 functions being composed, I have 3 products here, right? The derivative of the outside times then the derivative of the inside, which is the middle function, because that's still a composition. So the derivative of the middle, and then times finally the derivative of the most inside function. So here, how many functions do you see being composed? Because then that's going to tell you how many products you're going to have, how many derivatives you have to take. And so one of the things that I will do is rewrite it. So I would say y is equal to cosine of, what's this? So I have a cube root, so that's going to be to the third. So stuff to the 1/3, and then I have sine of tangent of 3x squared plus 1. So every time that you find yourself saying of, that is a composition of functions, right? And be careful, this isn't cosine times that. This is the cosine of something. So cosine is a function. So let's see. Let's try to number them. The outside function, so that's the first one that I'm going to take the derivative cosine of, and then the stuff follows, of the cube root. So then this one is my second function that I'll be taking the derivative, so 1/3. And then what's the next one? Then sine, right? So then 3, then tangent will be the 4th one, and then 3x squared plus 1 will be the 5th one. So when I take the derivative of this y prime, I'm going to have how many products? I have 5 functions being composed, so I'm going to have 5 different products. So the derivatives of each of those, 1, 2, 3, right? So then here, and I'm going to be again very informal, so it's going to be the derivative of the most outside function times the derivative of then the next one function, and then the next one, and then finally the most inside. So can we complete this? I don't know that I have enough room to write all of this. So y prime, the derivative of cosine, what's the derivative of cosine? Is negative sine of the stuff left alone. So in here, right, is I'm going to write what I had on the inside there. So sine of all of these. So sine of tangent of 3x squared plus 1 to the 1/3 times then the derivative of the next function, so it'll be the 1/3. So 1/3 stuff to the negative 2/3. And what's going to be on the inside is the inside of the cube root function. So sine of tangent of 3x squared plus 1. And then times, so that was the derivative of cosine, the derivative of the 1/3. Now the derivative of sine is cosine of the inside of this sine, so tangent of 3x squared plus 1. And then, so I have 1, 2, 3 products. I have 2 more to go. Times, so we did the derivative of sine. Now the derivative of tangent. So I'm on the 4th one. What's the derivative of tangent? The derivative of tangent is secant square of stuff, the inside left alone. And then lastly, times the 5th one, the derivative of the inside. The derivative of 3x squared plus 1 is 6x. Phew! So this is a pretty massive chain rule, but that's because there were 5 functions being composed. So I hope that makes sense about the importance of recognizing how many functions are being composed and what you do with them. Now notice that when I take the derivative of the first one, the most outside function being the cosine, the inside, so I take the derivative of cosine, which is negative sine of, the inside stays the same. Notice that it's not a chain rule of derivative continuously. I don't do the derivative of cosine, the derivative of sine, the derivative of tangent all in one step. It is the derivative of the outside function, the inside left alone. So the derivative of cosine is negative sine of the inside of the cosine. Notice that it's left alone. And then times, then the 1/3 is my next function. The derivative of x to the 1/3 is 1/3 stuff, the inside left alone, to the negative 2/3. And so that's kind of like what the chain rule is doing, right? So you take the derivative of each function that's on the outside while leaving the inside of that function intact. You don't touch it, and then you continue taking the derivatives until you make it all the way to the most inner function, and then that is the last derivative that you take. The chain rule is a lot to take on, and it can be confusing, so I encourage you to practice, do the examples from the textbook. The homework might not be enough to practice, but you want to make sure that you get the chain rule down. It's really, really important. It is one of the major concepts in Calculus 1 that is going to stay through Calc 1, Calc 2, Calc 3, differential equations, physics. So it's really important to get this concept down. In your ebook, you have access to the homework problems that are on there. So I would suggest try those. Try the odd ones so that then you can see the answers in the back of the book. But there's no, in the ebook, there's not really a back of the book, right? So just go to the answers to selected problems. Towards the bottom of the ebook menu, you'll see a page that's called answers to selected homework problems. And then if you do the odd ones, you should be able to then check your answer and see that you're doing them right, or you can just try to practice extra homework. All right, so let's try this one. Find the derivative of y equals the quantity tangent x over x plus 3 to the 3rd power. So this one's not as bad as the previous problem. How many functions are being composed here? And hopefully you're only seeing 2 functions being composed. So we have the outside function, the cube, and then the inside function. So let me write them a little differently. Let's say instead of y, I'm just going to say outside. And then the inside function is that tangent x over x plus 3. Now this, because this is a division of functions, right, then this is lets me to believe that I'm going to use the quotient rule when finding the derivative. So I'm going to need the quotient rule for that one. So find a derivative. So I'm going to say y prime then is, I have to use the chain rule because I have a composition of functions, so it's the derivative of the outside. So the derivative of something cubed is 3 to the decrease the power by 1. The inside left alone, so I'm going to have tangent x over x plus 3 times the derivative of the inside. And then in this derivative, we need to use the quotient rule. So let's do that. So this tangent x over x plus 3 squared. So again, notice that I took the derivative of the outside, leaving the inside alone. I'm not doing this quotient rule and putting it inside. So I don't do the derivative of the outside and then inside do the derivative of the inside. That's not how chain rule works. You do the derivative of the outside, the inside stays the same, then times the derivative of the inside. So now here, I need the quotient rule. So what is quotient rule? So low d high, so x plus 3 times the derivative of tangent x minus, so low d high minus high tangent x times the derivative of x plus 3 high d low all over the bottom square. And so let's do those derivatives. So I'm going to have 3 tangent x over x plus 3 square times, let's see, so I'm going to have x plus 3 times the derivative of tangent is secant square x minus tangent x times the derivative of x plus 3. The derivative of x is 1 and the derivative of 3 is 0, so just times 1, so we don't need to write that one, over x plus 3 square. Can I cancel these? No, right? And this is from the one of the prior videos. I said be careful because we have a subtraction here. So you would have to do this whole quantity, the subtraction, before you can divide with the bottom. So this is as far as we can go. There's nothing that I can factor or do better to simplify, so we can just leave it like this. And some of these answers are just not going to be very nice to simplify, so you can just leave it. All right. In the next video, I'm going to do some examples involving the equations of tangent lines and normal lines. So a normal line is essentially a line that is perpendicular to the tangent line. So that's on part 3 of the chain rule video series.